Lecture 1. In this lecture, we will talk about number systems. We have here 5 number systems: decimal, binary, octal, dual decimal, and hexadecimal systems. For decimal numbers or decimal system, we use the regular numbers that we know in our real life. 0 to 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. The total number of these numbers is 10. This is why we call this system decimal system, or we call these numbers decimal numbers, decimal 10. Binary system uses only two numbers 0 and 1. 0 and 1, the total number of symbols is 2. This is why we call it binary system. Binary, it means 2. Binary system or binary numbers. Octal system consists of 8 numbers, 8 symbols, only 8. This is why we call it octal system, because the total number of symbols used in this system is 8. Dual decimal systems, 12 symbols, 0 to 9, and then 10 and 11, we denote to 10 by A, 11 by B. The total number of systems is 12. The hexadecimal numbers contains the same collection of symbols as in dual decimal, but it continues with C, D, E, F that corresponds in decimal to 12, 13, 14, and 15. The total numbers of symbols is 16. Hexa, or this is why we call it hexadecimal system. This example is for decimal numbers. As we see, we have this decimal number, and this subscript indicates that this number is decimal. This number is a decimal number. This is a binary number, and see, this subscript denotes that this number is a binary number. All numbers here are zeros or ones, so you cannot see 2, 5, A or B, only zeros or ones. Octal system. This number is an octal number, and this subscript indicates that this number is octal system. You can't distinguish between this number and the decimal one, the decimal number, even the dual decimal number or hexadecimal number, because all of these numbers, decimal, octal, dual decimal, and the hexadecimals, have the same symbols like these ones. So you have to write 8 here just to understand that this number is an octal number. Dual decimal number, this number is a dual decimal, and 12 here just to say that this number is a dual number, a dual decimal number. This number is a hexadecimal number, and this subscript is 16 that indicates that this number is hexadecimal. You can understand yourself that this number is a hexadecimal number because this symbol E is used by only this system, the hexadecimal system. These numbers contains two parts, the whole part and the fractional part. We want to convert all of these numbers in these examples into decimal numbers. How can we do that? We will rewrite these numbers in this way, the same number. This is the same number as this one. 244, but we ignored the point here and continued writing the fractional part, 528. We will do the same thing with this number and the rest. But just remember that this part is the whole part of these numbers. See, 244, this is the whole part. This number is the whole part, 357. This is the whole part, 28. And see here, we converted A into 10, B into 11. We did the same thing here, A to 10 and E to 14, because we cannot perform these arithmetic operations with such symbols. These are the whole parts of the numbers, and these are the fractional parts of these numbers. The first step, we will use these numbers that represent the total number of each system, 10, the total number of decimal, 2, the total number of binary, 8, the total number of octal, 12, the total number of dual decimal, and 16, the total number of the hexadecimal symbols used in this system. We will use these numbers to multiply our numbers in this example. 10, say we use 10 to multiply all of these numbers. We will do the same thing for the rest of the numbers in these examples. We will multiply these numbers by this number, that by 2, the octal decimal number by 8, the dual decimal by 12, and the hexadecimal by 16. This is the first step. Multiplying these numbers by these numbers that represent the total number of the corresponding system. The second step is to raise these numbers 10 to 8, 12, and 16 to powers. Why? Because we used these numbers as bases. As you see now, we raise them to numbers. So these numbers that represent the total numbers of each system here are used as bases for performing the conversion to decimal numbers. What we did here, we started with this whole number from 4, the first number in the right side, 4, that we multiplied it by 10 and raised it by 0. We started with 0, then 1. You see, increase the number, the power, 0, 1, 2. We stop here because the last number here in the left side is 2. This is why we stopped here. You start with 0, and in our example, we start with this power 2. What about this part, the fractional part? You continue, but in reverse direction. 1 before 1, 0. 0 before 0 is minus 1 as a power of 10. Minus 2 as a power of 10, of course, and 10 a power minus 3. You remember, now I will draw the coordinate, only the x-axis coordinate. To explain this, you need, this is the origin point, 0. And to the left of 0 of the x-axis coordinate, 0, for example, this is 1, this is 2, we scale it by 1. We increase by 1, 1, 2, 3, etc. The right side, the negative part, minus 1, minus 2, minus 3, etc. This is what we have done here with the powers. 0, 1, 2, 3. In the left side, this is for fractional part, I mean. you use -1, -2, -3. We will do the same thing. Next, sum up all these numbers. The final result is this one. As you see, is exactly the same number as the original one. Why? Because we try to convert a decimal number into decimal number. This is why we got the same result. But this is not the same case with the rest of the systems. Let's see this number. You see, this is the final result. This is a decimal number that corresponds to this binary number. The same thing for octal, dual decimal, and hexadecimal. You can check your result using your calculator. Now we will perform opposite operation. We will convert decimal number to binary number. We will use repeated division by 2. Before we start, I want to remind you about the terminology of the division operation. We call this number here dividend, this one divisor, the result here quotient, and the result here remainder, 244 undivided by 2. Why 2? Why 2? Because we want to convert it into binary number, and we remember the base of the binary number is 2. This is why we used 2 as divisor. You see? So 244, this is the dividend, our dividend. The number 2 here is the base of the binary that is required to convert it to, which is our divisor. The result is 122. This is our quotient. Multiply by 2, and this is the result of the multiplication. Then subtract. The first remainder is the first number that appears as a result of this operation, the repeated division by 2 operation. This is our first binary number. We take the quotient 122 and repeat the division by 2. So we took the quotient. Now the quotient will be our dividend, and the divisor still as is 2. The quotient is 61, multiply it by 2, subtract both numbers, the result will be 0. And this will be our second binary digit. See, we wrote it in the left side of the first number, the first binary number. Continue. So the quotient will be our new dividend here. The quotient is 30 multiplied by 2, 60. The new remainder is 1. We will add it to our set of digits, binary digits. As you see, you cannot obtain but these zeros or ones. You cannot obtain 2 or 3, for example, only 0 or 1. We continue with repeated division by 2. Again, we use the quotient as a dividend and divide our 30 by 2. The quotient is 15 multiplied by 2. The result is 30. Subtract both numbers. The remainder is 0. And again, add it to the left side of our new set of binary numbers. We continue. The quotient is 15. The result is 1. And again, add it to the left side. 7 divided by 2, the quotient is 30, multiply it by 2, so the result 6. The remainder is 1, and add 1 to the left side. The quotient is 1 multiplied by 2, the result is 2, subtract them, the remainder is 1, add it to the left side. 1 is our new quotient, divided by 2, the result is 0, multiplied by 2, the subtract 1 minus 0. The result is 1. Add this remainder to the result and stop at this point. Stop it. Why? Because the quotient is 0. So when you reach to this result, when the quotient is 0, you stop the repeated division by 2 and get the numbers in this direction. 1, 1 from the last remainder to the first one. This is your binary number result that corresponds to this 244 decimal number. Another way to do repeated division by 2. 244 divided by 2. The result is 122. You write 122 here. The remainder is 0. Repeat the division by 2. Divide 122 by 2 equals 61. This is the quotient that we have obtained, 61, and this is the remainder 0, because we obtained 61, exactly 61. Again, we will divide 61 by 2. The result now is not exactly 30, it's not an integer number, it's 30.5. What we do in this case, we take only 30, the integer part, the whole part, 30. And because this is not only a whole number, it's with fraction, this is why we will have 1 as remainder. Here is 1. Our remainder is 1. Now, the quotient is 30, so you will divide 30, not 30.5. You will divide 30, not 30.5, 30 as a quotient divided by 2. The result is 15. Remainder is 0. 30 divided by 2. 30 divided by 2. The result is 15. And because the result is 15, only an integer number, so the remainder is 0. Repeated division by 2. We will divide 15 by 2. The result is not an integer number. It's 7.5. So what we do, we write the result as 7, not 7.2.5. It's only 7. And because there is a fraction part, the remainder will be 1, not 0, 1. 7 divided by 2. The result is 3.5. So we understand now that when the result is not a whole number, not an integer number, comes with decimal part, with a fraction part, so the remainder will be 1. And you write here only 3. You take only the integer number. 3 divided by 2. The result again is 1.5, not an integer number. So you write only 1. You take only 1 from here. And because we have fraction number here, the remainder will be 1, not 0, 1. Divide 1 by 2, repeated division by 2. The result is 0.5. We take just this part, the whole number, the integer part. We write here 0. And because the fraction number is there, we have here decimal part, fraction part. We write here 1 as a remainder here. Now, because we obtained 0 here, we stop at this point, and this is our binary number. Now, we will talk about conversion to other bases. We will divide 244 by 8. This is the result. Multiply 30 by 8, 240. subtract them, you will get this number. Now we will take this quotient 30, we will use it as a dividend and divide it by 8. This is the result. The quotient multiplied by 8, the result is 24. Subtract numbers, you will get 6. You will use this number as a second number of your octal number. We continue. We will use the quotient as usual as a dividend divided by 8. The result is 0. Multiply 0 by 8, you will get 0. Subtract 3 minus 0, you will get remainder 3. Add it to the left side, and that's it. Stop here. Why? Because the quotient now is 0. This is your number, the octal number that corresponds to this decimal number. The second example is to convert the decimal number, the same decimal number, to hexadecimal system, to hexadecimal number. So we understand now how we divide the number, by which base. The base should be, of course, 16. We start now with our repeated division by 16. 244 divided by 16, the result is 15. This is a quotient. 15 multiplied by 16, the result is 240. Subtract both number and you get your first hexadecimal number. Get the quotient 15, use it as a dividend to the next step, divided by the base, which is 16. The result is 0. Multiplied by 16, 0. Subtract both number 15 minus 0, you will get your final decimal number. But here, as you see, this is a decimal result. Because you want to convert the number to hexadecimal, you need to convert this remainder, this number, into its corresponding hexadecimal number, which is f. So you add f to the left side of the first hexadecimal number. That's it. You are done with your hexadecimal number. Don't forget to add the subscript here, 16. The last example is about getting dual decimal number from 244. This is the result, and carry on until you reach your final result, which is 0, and stop at this point because this is 0. The thing that you have to know, that all remainders should not exceed the set of the system that you are working on. For example, here we want to convert into octal, so you should not get any number that exceeds 7, because this is an octal. If you obtained, for example, 8 or 9, so that means there is something wrong in your division process. You have to repeat the division at that step. So what you have here should not exceed the system that you are working on. Here we will not get 16 or 17. The same thing with dual number. You will not get 15 or 16. The second approach is going through another system via binary system. We write the same number that we have got in the previous example. We will write it here. This number is the same as this. This is the binary form of the decimal number 244. Because we want an octal number as a result of this conversion. Remember that the octal number, the maximum number in the octal number is 7. That we write it 7 in octal. That we write it in binary using these 3 digits in binary form. These 3 digits, and this is the maximum number. See how many digits we have with this maximum number of this octal system. We have 3 numbers only. We will use this principle to separate this binary number. We will separate them by 3 digits. 3 digits here, 3 digits here, and 3 digits here, but we have only 2 left here. What we do? You have to add 1 0 to the left. That will not affect the whole number. So you should add 0 to get 3 digits. Then the second step, what you do, you will convert each 3 digits into octal. You multiply this 0 by 2 of power 0 plus 0 multiplied by 2 of power 1 plus 2 of power 1 multiplied by 1. And the result will be 4. Then you go to the second 3 digits. You will get 6. And this one, the last one, is 3. This is the result of your octal number via the binary number. But remember, if the last digits were 2 digits or 1 digit, the rest you have to add to the left are 0 or is 0. In our case, is 1 0. If you have only 1 here, you should add 2 zeros here. So this is the reason why we separated them by 3. Or another way to understand this, why we have separated them by 3. The octal number, it means we have 8 symbols. 8 symbols. 8, this corresponds to 2 of power 3 in the binary system world. The power is 3 here. 3, it means you are using octal system. 3. This is why we separate them by 3. So you use this principle or this one to understand why we have done this step to reach to our octal system. Hexadecimal number. How we convert this to hexadecimal? Via binary number. The same result here, we will use it, but we will separate not by 3, but by 4. The maximum number of hexadecimal is 1111 in binary, which corresponds to the maximum hexadecimal number F. This is why we separated the binary number into 4. 4 and 4. You see, if the last digits were, for example, only 1 here, you will add 3 zeros to the left. And you know what to do. If you have 2 or 3 digits only, you complete the 4 digits with zeros. Another way to understand why we separate them by 4, that 16, this is the hexadecimal system, it means 2 of power 4, that corresponds to 16. So the power of these 2 is 4. This is why we separate them by 4, to use this step to convert them to the required hexadecimal number. So 0010 2 of power 0 multiplied by 0 plus 2 of power 1 multiplied by 0 plus 2 of power 2 multiplied by 1 plus 2 of power 3 multiplied by 0. The result is 4. You do the same thing with this. The result is F. You will get here 15, but you should write it into hexadecimal form, in hexadecimal symbols. Yeah, this is our hexadecimal result. We will learn how we convert into different systems from decimal fraction to different systems. We start with the conversion of decimal fraction to binary system. We will take this fraction number 0.625 in decimal. We start by multiplying the original number by 2. The result is 1.250. We will get this just the integer part. We get it aside. This will represent our binary number. Then we will take the fraction part only. We will ignore this integer part. We will get this part, which is 0.250, and repeat the multiplication by 2. We will get this number. We will get this part as a binary number, and again we will use this part which is 0.5 and repeat the multiplication by 2. We will get a 1. We will take this out as our binary number, and here we stop. We stop when we get 0 in the fraction part. How we get the number, how we collect the result of binary numbers? We start from the first remainder to the last one in this direction. How we arrange them horizontally? We arrange them in this way. You see, in this way, from the left to the right. Don't forget to write 0 point, because this is a fraction number. The result also is a fraction number. So 0 is here, it means stop. Now, another operation for another system. Conversion from decimal fraction to octal system. We will use repeated multiplication by octal by 8. Repeated multiplication by 8. This is the result 5.00. We will take this aside as the first octal number. We will take this part, the fractional part, to repeat the division, but we stop at this step, the first step. Why? Because we got 0 here. So we stop the operation, and this is the only number that we have. We write it here. So we have 5, but you have to write 0.5. 0, it means we stop here. Now converting 0.625 to a dual decimal system. 0.625 multiplied by 12 as a result, and you do the same thing and you collect the numbers in the same way. And finally, this is a conversion of decimal fraction into hexadecimal 10, but you know you have to convert this number into this number 10 into its corresponding hexadecimal number to add it to the final result. So we have a here, or 0.a actually, because it's a fraction hexadecimal number. We stop at this point because the fraction part is 0. Arithmetic operations. Now we will learn how we can perform arithmetic operations with different systems. For example, in this example, we need to perform addition to add this octal number to this hexadecimal number and the result to be in octal form. How can we do that? We have two methods. Method one, the first method, the first thing you do, the first step is to convert each of them into decimal number. See, this is octal, this is hexadecimal. We convert them to another different system that is easier to understand and to process in our arithmetic operations. The first step is converting octal to decimal. This is what we are going to do. We will convert this octal number into decimal. We multiply each of these digits by 8 and raise the first one on the right side to 0, increase the power 1, 2 to get the decimal number. 444, this is the decimal form of this 674 octal number. We will do the same thing with the hexadecimal number. We multiply this number after converting it into its decimal form, 12. We multiply it by 16 and this number by 16. The first one on the right side, we raise it to power 0 and this one to 1. 16 of power 0 is 1 multiplied by 12, this is 12. 16 of power 1 is 16 multiplied by 1 is 16. 16 plus 12, this is 228 in decimal form. Now we are able to add both of these numbers in their decimal form. It's too easy to do that. So we add both results. Sum up the decimal results. The result is this. Why? Because we add 444 to 28. This is the result in decimal. But the question asks to get the result in octal form. The second step is converting the decimal result into its octal form, and we know how to do that. Take the decimal number and use repeated division by 8. And this is the result. We stop at this point because the quotient is 0. And you know how to arrange the result from left to right. The second method, we select one of these different systems and convert it to the other one. What we did here, we will take the hexadecimal number and convert it into octal. Then we will sum up the octal numbers. This is easier than taking this octal and converting it into hexa, because we should do another process. Another arithmetic operation is converting the result into octal. So we will save our time and convert the hexadecimal into octal. This is what we are going to do. Hexadecimal to binary. 0011, this is C, this is 12. 1 is the result in binary of this one in hexa, but you know you have to add another three numbers to complete 4 digits here because you are converting from hexa into binary. Now what we do, we go to the second part. The second step, we take this binary number and convert it into octal. And you know how we do that? We take every 3 digits and find the octal number. 001, 3, 4, 110, it's a 3, and finally 000 is 3. Or we can write it 3, 8. This is our final result in octal. Now we can sum up this 3, 4 in octal, which corresponds to this one, with this number, because both of them are octal numbers. We will do that. 730 is the result. The result is the same.